Now that we have the idea of polygonal paths and quadrilaterals, we can define a general polygon. So with a quadrilateral, we needed a simple closed path of order 4. For polygons, we need a simple closed path of any order. Our only restriction is that n needs to be greater than or equal to 3. We can only have simple closed polygonal paths of order n, where n is greater than or equal to 3. And just like with quadrilaterals, I really want to consider convex polygons, which have the same idea and definition as quadrilaterals. If I expand out any one of the sides, the entire polygon should be on one side of that line. And I'm even going to go a little bit further. The real subclass of polygons that I want to consider are regular polygons. The idea here being that all of the sides are equal and all of the angles are equal. Let's look at how we can construct these regular polygons. In order to do this, we need to start with a point that we're going to call O, and we're going to extend out a line segment to our point P1. We then do a congruent line segment to that one, and we call this P2. So these two are congruent. We do another point P3 such that not only do I need this side length to be congruent to the other two, I need the angles to match as well. So these angles will be the same. We can then keep going. We construct P4, once again to be congruent and the angles to match, and we can keep going all the way around until we get to our very last point, Pn. So all of our sides will be congruent, and we're constructing these so that each angle, so each one of these central angles, is 360 over n. So we need to verify that this very, very last angle does actually match the rest. So I need to consider the measure of PN, O, P1. Once I've constructed all of these congruent angles, this last one is already determined for me, so I need to make sure it's congruent to all of the rest. We know there's 360 degrees in a circle, and I know I have already accounted for n-1 of these angles, which are all the same as the measure of P1, O, P2, the first angle. Simplifying this, I have 360 times n-1, and this angle here we just said was given by 360 over n. Multiplying this out, I get minus 360 minus 360 plus 360 over n, which is 360 over n. So it does verify that the last angle matches the others. All of those angles are congruent, and my actual polygon comes from drawing the polygonal path between these vertices here. This construction that we just did produces a regular n-gon, where n is greater than or equal to 3. So essentially what I've just shown is that no matter what, I can construct these regular n-gons, so regular polygons do exist. In addition, since each one of the vertices of my polygon was the same distance from that central point O, a regular n-gon can be inscribed in a circle. So no matter what size polygon I start with, if it's regular, I can find a circle that passes through every single vertex.